As an interesting application of the concept of center of mass, let's consider the famous Fosbury flop. What is it? It's a way it's a way to clear the bar in a high jump competition. It was invented by an American athlete by the name of Dick Fosbury. That's what we call it, the Fosbury flop. Okay, here's how it works. Normally, when a person clears a bar in a high jump, okay, the easiest way to do that is by running forward and lifting your legs horizontally up like this, and your center of mass is somewhere here. And your legs, of course, are below the center of mass. Your head is above the center of mass, and the bar has to be placed below the center of mass, actually below the lowest point in your body, which is this point. Okay, so you can clear the bar from here to there. This is the height h. You can jump over. This is rather easy to do, but you see, you have to lift your center of mass considerably above the bar in order for your body to clear the bar. This is certainly not the best way to clear it. Later on, people invented a different way of doing that, and that is what they do is when they clear the bar, they face downwards, and the body is like a spread eagle. Okay, so the body is like a horizontal pancake at this moment. So here is the head, and you have these are the two arms, and these are the two legs like this. It's a pancake, more or less horizontal when you clear the bar. So the center of mass, of course, is somewhere in the plane of the pancake, which is right here. But since the pancake, which is the surface of your body, is pretty much horizontal, you can place the bar just a little bit below it, and you can still clear it. Okay, so the bar can be placed right there. Right? Imagine this entire body, it drapes. It's like almost like a horizontal plane above the bar, just slightly above the bar. You see, in this case, in both cases, you have managed to use your muscle power to lift the center of mass about the same distance from the ground. This is about the same distance. Yet here, h is greater. You can place the bar higher. You can clear. You can clear better. Okay, this is when you're face down. You see, when you're facing down, if you want to bend your legs, you can only bend your legs upward, right? Because you're facing down, right? You can only bend your legs upward. Now, the thing about it is that when you bend your legs upward, what happens to the rest of the body? The rest of the body have to go down a little bit. Why? Because the center of mass is some sort of average position. Okay? So you look at the vertical position of the center of mass. This part of the body, which is, your lower legs are going upwards. The rest of the body have to go downwards to balance it out. So you certainly don't want to bend your legs upwards, because that will lower another part of the body. Maybe you will trip the bar. Okay, neither of these is as good as the so-called Fosbury flop. And here is a picture of the Fosbury flop. You see this picture here. This is a Fosbury flop. So instead of facing downwards towards the ground, you're facing upwards. Your body is like an inverted U, okay? Like an inverted U. Again, the center of mass position is some sort of average position. If your body is an inverted U, you have low points of the body, high points. The actual center of mass is somewhere in between, maybe here. Okay, like an inverted U, somewhere here. Not too low, not too high. But the bar is like this. You see, the bar can actually be positioned above the center of mass. Why? Because this is a very clever thing. You're not clearing your entire body over the bar all at once, are you? You are clearing your body over the bar segment by segment. What you do first is this is in fact in the middle of the jump. In the beginning of the jump, your 2 feet are the highest position. The 2 feet are lifted above the bar. Once the 2 feet cross, it's the middle part of the body that's crossing the bar, which is right here. But by that time, the 2 feet are already considerably below the bar. So even though the middle section is above the bar, the 2 feet are considerably below the bar, so is the head. So the center of mass is still below the bar. And the next moment, as you know, as the 2 feet go even lower, it's the turn of the head. The head is the only part of the body that's above the bar, but the rest of the body is already considerably below the bar, so the center of mass stays below the bar. You are clearing the bar segment by segment while managing to managing the the position of center of mass to be always below the bar. Why is this advantageous? Because if you still lift your center of mass by the same amount, which is about here, okay, using an inverted U like this, you can position, the center of mass is here, okay, you can position the bar here. See? You clear it segment by segment. Even though the center of mass is lifted by the same amount, this segment is above the bar, next one, the head is above the bar, and so on. So you can clear the bar with an even greater height. Okay, this is more advantageous than the second case, because the second case, when you face down, you can only bend your legs upward. It doesn't help you at all. Here, you look skyward. You can bend your legs and arms downward, and that actually helps the rest of the body to go above the bar. So that is the so-called Fosbury flop. And ever since it was invented, this has become the standard way of clearing the bar for all professional athletes in a high jump competition. Okay, now that we know the center of mass is an important special point in the system, let's locate the center of mass. Okay, how does one locate the center of mass? We are looking at two kinds of examples. One is the system is made of discrete set of particles. Let's say here a dumbbell-shaped object, M1 and M2. And the second type is when the system is made of a continuous object. Okay, here's the first type. You got 2 point masses, M1 and M2, separated by distance L. The L, this segment here, from here to there, is massless. Let me choose a coordinate system centered at M1, for example. We all know by common sense, if M1 equals M2, where is the center of mass? If all the masses are equal, then of course, they have equal weight in determining the position. This position of the center of mass will be right in the middle, right? Half of L. Okay, but if M1 is not equal to M2, then the center of mass will be closer to the more massive side. Let's see, how do we calculate that? Well, XCM equals 2. By definition, M1 X1 plus M2 X2 over the total mass, which is M1 plus M2. Now in this case, X1 is the position of the first mass, which is 0. X2 is the position of the second mass, which is L. So this is just equal to M2 L over M1 plus M2. Which makes perfect sense. If M1 and M2 are equal, you got M2 over 2M2, which is 2, so that you get L over 2, right? If M2 is greater than M1, then this ratio M2 over M plus M2 is slightly greater than 1/2, is greater than 1/2. The center of mass will be somewhere closer to this side, and so on. So this is how you calculate center of mass for a set of discrete particles. Let's look at another simple example, this time involving a continuous object. I still have something of length L, but this time the mass is evenly distributed all the way from here to there. Where is the center of mass? Well, again, by symmetry, if the rod is uniformly distributed, then the center of mass has got to be in the geometrical center, right here, right? Again, it's half of L, but let's not take that for granted. Let's actually work it out. The idea is I'm going to cut this thing into small pieces. Okay, I'm going to cut it into small pieces, say this piece from here to there. This little piece here, mass dm. The distance between this little piece and the origin is x. How does it contribute to the center of mass? Well, the center of mass, xcm, for continuous object is 1 over the total mass, x dm. That's the formula we use. Okay, and in this case, what's dm? That's the question. What's dm? Well, dm is a fraction of the total mass m. And what fraction is it? That depends on, you see, is 1% of the total length L. Then should the total mass of the rod m, because it's uniformly distributed, right? So we conclude that there is a proportionality dx over L must equal to dm over the total mass. Okay, dx is the length from here to there. This allows you to solve for dm. dm is m over L times dx, so it's m over L dx. X runs from 0 to L, 0 to L. Let's see. Do we get half of L? We better do. M and M cancels. It's 1 over L, and then x dx, you integrate, that's 1/2 x squared. X runs from 0 to L, so the answer here is 1/2 L squared divided by L. Indeed, we got what we wanted, 1/2 L. Okay, so this is an example of a one-dimensional continuous object. Now let's look at a two-dimensional object. A right-angled triangle. Let's say the total mass is m. And the thing is, the mass is uniformly distributed. Okay, the length from here to there is a, the height is b. If this length from here to there is a, so it's going to be somewhere above, somewhere over half of a, but less than a. Okay, less than a. A is all the way here. So xcm is somewhere between half of a and a. Where is it? Well, again, I have to divide this into pieces and consider the contribution of each piece to the center of mass position. And the thing about it is that if you're looking for xcm, okay, the x coordinate at the center of mass, then you realize that every point along a strip like this, a strip that's parallel to this line here, every point along this strip has the exact same x coordinate, right? Same x coordinate. So they contribute similarly to the center of mass xcm. So as far as xcm is concerned, remember the formula we use, 1 over m x dm. Every point on this strip has the same exact x. Okay, so instead of cutting it into infinitesimally two-dimensional small dots, why don't I cut it into strips? Because after all, every strip, within every strip, all the point on every strip has the same exact x. So I'm going to just imagine cutting this thing into strips. Let's see how much does each strip contribute to xcm. Okay, and that has to do with dm. X is the same from here to there. What's dm? dm is the mass of this red strip, and that has to do with the area of the strip. If this triangle has a uniformly distributed mass over its area, then just like we learned in the previous problem, if this red area is 1% of the total triangular area, it should also contain 1% of the total mass. So this time, the proportionality should read this, like this. dm, which is the mass of the red strip, over the total mass m of the entire triangle, must equal to dA, the area of the red strip, over the area of the entire triangle A. Okay, let's do a little calculation here. What's dA? dA is height times thickness. Okay, base. Base is dx from here to there. So it's dx. What's the height? What's the height? The height, let me call it y here. From here to there. Let's call it y. Okay, this is dx. What is y equal to? Okay, let me call it y first, and let me work it out later. The total area is 1/2 base times height, of course. That's 1/2 AB. Right? 1/2 A times B. What is y? You know, there's a constant proportionality. From the distance between here and there is x. Isn't it true that y over x equals b over a? Right? And therefore, y equals xb over a. Let me plug it in here. dx times y, which is xb over a. And let me divide this by 1/2 AB. Okay, let me finish all the algebra here, which I can then plug in there. So what do I have here? B and B cancels. A and A cancels. And actually, B and B cancels. This is A and this is A. They don't cancel. They get A squared. So dm over m equals 2x dx over a squared, which I plug in here. See what do we have? dm over m. Okay, there's dm over m, which is 2x dx over a squared. So 2x dx over a squared. Don't forget there's another x, so there's an x squared here. X runs from 0 to a, 0 to a. So what's this integral equal to? Okay, it's 2 over a squared. X squared dx, that's 1/3 x to the power 3. isn't it? X goes from 0 to a, so the final answer here is 1/3 a squared, a to the power 3 divided by a squared, so the answer is 2/3a. Indeed, we found the answer to be somewhere between half of a and 1a. It's actually 2/3 a. So it's 2/3 of the way from this sharp angle, sharp corner, 2/3 of the way down before we found this line. That is XCM. Okay, knowing XCM, do we have to solve for YCM starting from scratch? No, we don't. Everything is symmetrical, isn't it? Because from this sharp angle, you go 2/3 of the way down before you see this right angle, you get XCM. Same thing here. You start from this sharp corner, you go 2/3 of the way down, which this total distance is B, okay? 2/3 of the way down, you will find YCM, right? So from here to there from here to there is 2/3 of the way, which is 2/3 of B. So what's the distance between here and there? That's 1/3 of B, right? So therefore, I found YCM to be 1/3 B. From the base to the YCM is 1/3 of the total length from here to there. It's 1/3 of B. So the center mass is somewhere here. Somewhere here. 2/3 of the way down, 2/3 of the way down. That makes sense.